Now since we know how to use the compiler scope, let us use it to look inside an optimizing transformation. We'll start with a simple transformation called loop invariant code motion that optimizes the loops in the program. This optimization is also implemented as a transformation phase in the backend, and the compiler scope gives the view across this phase. Let's spend some time understanding the optimization before viewing it with the compiler scope. Loop invariant statements are the computations that do not change within a loop. For example, in the code snippet shown on the right, the statements marked in red are loop invariant statements. Observe that the result of these statements do not change within a loop. It is easy to see that the variables a and x will always have the same value irrespective of the loop iteration. Thus, with this optimization, the loop invariant statements can be moved in front of the loop. The same code snippet is shown on the right with the optimization. Observe that the loop invariant statements have been moved from inside the loop to the front of the loop. Since there are less number of statements inside the loop, the program will run faster. This is a simple and yet effective optimization. In some cases, this optimization can make program about 50 to 80% faster. The same optimization when seen over flow graphs looks as shown. The statement in red are the loop invariant statements and have been moved from inside the loop to the front of the loop. The same example when seen with the flow graphs of Phoenix IR are shown here. The statements in red are loop invariant statements and have been moved from inside the loop to the front of the loop. This slide shows the flow graph as seen in CompilerScope. The right hand side flow graph is for the complete program, and the region of flow graph marked in red circle corresponds to the flow graph shown on the left. The flow graph on the left corresponds to the code snippet before the optimization. This slide shows the expected change due to the loop invariant code motion optimization. The region of flow graph between 3 to 4 is a loop, and since this optimization moves the invariant statement from inside to the front of the loop, we expect to see some code motion from block 4 to block 10 after the transformation. Let us monitor the changes done by this transformation phase. We see that the block 4 has been highlighted after the phase, so there must be change in this block. Clicking on the block 4 in both the flow graph shows the corresponding code in the code window. Observe that the statements marked in red in the left window are not present in the right window. Also note that there are loop invariant statements. Thus we see that the loop invariant statements have been moved from block 4. Let us now see the changes in block 8 and block 10, as block 10 has been highlighted. Clicking inside the block 10 shows us the code corresponding to these blocks. Observe that the statements marked in red in the right code window has been added after the transformation. Also note that these are the same invariant statements that were moved from block 4. Thus we can see that the loop invariant statements have been moved from block 4 to block 10 after the optimization. With this example, we saw how easy it is to see the effect of transformation with CompilerScope. CompilerScope helped us to visualize the changes in IR through flow graphs, and also it's the change highlighting feature that helps us to easily locate the changes. The CompilerScope works with the Phoenix based backends, and there are many advantages of using a Phoenix based backend. The Phoenix backends are modular, as different phases combine together to make entire system. They are layered and the phases are built on top of one another. They are extensible as new phases can be added easily, and also Phoenix provides a lot of pre-built components for optimization analysis frameworks, which really helps to build backends really fast. Phoenix also facilitates CompilerScope in a number of ways. Its modular architecture allows CompilerScope to focus on one phase at a time. The IR based architecture of Phoenix makes it possible to compare IR across different phases, and the pre-built components such as APIs to view IR as flow graphs helps a lot in the display of CompilerScope. The CompilerScope can be used as an educational tool. It can be used to illustrate the process of compilation to students. It facilitates in understanding the components of backend, and it allows the individual transformations to be studied in isolation. It can also be used as a research tool to illustrate the impact of transformations on a backend, and it can also be used as a debugger to help to locate problems in the programs being compiled or the compiler backend. CompilerScope is a free tool, and it's free to modify, and it will be released with the next release of Phoenix. For more information about the release and Phoenix, please follow the link.